let's try something. Intuitively, describe what you think a picture is. And try not to do it in terms of technical terms, let's not talk about pixels or anything. Just in the abstract sense, what is a picture? What is an image? You might find that this is quite a challenging thing to define. Thankfully, in technical terms, things are quite a bit easier. And today, that's what we're going to be looking at. This video is again a two-parter. Basically, what we're going to do is today, we're going to try and understand a little bit about how images are actually written to disk, how we're actually encoding the images. And on Friday, we'll take a look at some, real-world image file formats and compare them against each other. This is a surprisingly deep topic, and we don't have a lot of time, so without further ado, let us jump into today's Random Wednesday episode. Hello and welcome back to another Random Wednesday episode. Now, while we might have some difficulty defining, what a picture is in abstract terms, well, thankfully in the computing world, things are a little bit better. Simply put, an image is simply a grid of pixels, in which every single pixel contains some color and brightness information. Our bigger challenge today is how do we actually represent this information, and how do we actually store this information on disk? Bearing in mind that a disk only records, bits and bytes. While this sounds simple, as it turns out, there are many different ways in which this information can be represented. So yeah, let's jump in and take a look at the most basic form. Since we know that an image is a grid of pixels and every pixel contains brightness and color information, well then, its representation on disk must kinda take this form, right? It has to be a storage of the brightness and color information of each pixel within the image. So using this as a working model guides us towards, the next couple of questions we need to ask ourselves. And that is, first of all, how do we represent brightness and color information? The most common method is to just grab your pixel and represent it in terms of red, green, and blue. And these are our three primary colors. Now, why we actually choose these three colors is known as the Tristimulus Theory. We've done a video about this in the past, so there will be a card on screen you can check out. Basically, the idea is these three colors are enough to basically trick our eyes into seeing every possible color we can see, so this is a good combination of colors to work with. So what this means is what you're storing in a file is basically everything in order from top to bottom. And that will be the red, green, and blue levels of the first pixel, red, green, and blue of the second pixel, and so on. By just representing everything in order, pixel by pixel, you will be able to store the entire image on disk. Of course, at this point we've only discussed, what to store, but not quite how to store it. So let's take a look at that. Obviously, we can't just store colors to disk. Instead, we have to represent them as numbers. And usually these numbers will represent the intensity of that particular color on that particular pixel. Of course, not just any number, right? We can't just store, random numbers willy-nilly on a disk and expect it to make sense. In fact, we can't even just represent numbers on their own on disk. Instead, we have to store them in terms of, this representation, which is your ones and zeros. In other words, a series of bits. Usually we group 8 of them together like this, and that will be known as a byte. The different combinations of ones and zeros basically can be converted to represent a number. So in fact, this bit string you're seeing on screen here represents the number 105. A byte runs from 0 to 255. And that basically represents all the possible combinations you can create out of these 8 bits, of course ignoring negative numbers. What does this have to do with our image representation? Well, this allows us to make a little assumption, and that is, what if every color channel is actually just represented as a single byte for each pixel? What that means is, if you have a pixel on screen, it's represented by 3 bytes, each one representing red, green, and blue levels. So yeah, that gives you your pixel, it's 3 bytes in terms of its size, or if you want to think about it in terms of bits, it is 24 bits per pixel. And this is a quantity that has significance. In fact, that also has a name, and that is color depth. And I've already used the term, it's measured in bits per pixel. Now, with this information, we can actually compute the size of an image. Here's how we do it. Let's say you have an image here. You need to know its width and height in pixels. In addition to this, you will need to know its color depth. First, we multiply its width and height, giving us the number of pixels within the image. In this case, there are 480,000 pixels within this image. Now, we know that every single pixel takes up 24 bits on disk, so we multiply that with the color depth. Now, this gives us a huge number here. It is 11.5 million, a very large number, but the unit is megabits, not megabytes, which is, the unit we are more familiar with. In order to get this in terms of megabytes, we simply divide this number by 8, and that gives us 1.44 megabytes. Now, this is completely by coincidence, but this image would nicely fit inside a floppy disk. That happens to be, well, the capacity of a floppy disk. So yeah, to quickly recap, our formula looks something like this. To know the size on disk, we take the width multiplied by the height multiplied by the color depth in bytes, if you want the result to be in bytes, something that is more common. Now, one thing may come to your attention, and that is a pretty large size. Now, to put things in context, this particular video has these dimensions. It's 1280 pixels across, and vertically it's 720. Assuming it has a color depth of 24 bits per pixel, what this means is every single frame gives us about 2.7 megabytes. Is that large? Well, that sounds kinda large. But don't forget, this is a video. We're gonna have to take the temporal component into account. In fact, a video is basically a whole bunch of pictures shown to you in quick succession, and this particular video comes to you at 30 frames per second. What this means is per second, you're showing 30 frames, and well, if we just, have the pictures as they are, every second of video is about 82 megabytes. Now, things are starting to look a little bit too big for comfort. Let's take this up one more notch just to really hammer in that idea. Per minute, there are 60 of this. And if we were to actually perform the multiplication, every minute of footage represented in this manner will run nearly 5 gigabytes. So think about it. What are some better ways in which we can actually represent our content? Now, clearly at this point, you're imagining that we can use some kind of compression, to make our file size smaller. But before we go there, let's first think about, whether there are some fundamental ways in which we can change up our representation to make things better. Clearly, there has to be at least one or two ways. Let's take a look. The simplest way we can do this is to simply assign less bytes per pixel. So as you can see, this is sort of, the calculation we've performed before. An image that is 800 by 600, with 24 bits per pixel, which for convenience I've represented here as bytes, will give us an image of size 1.44 megabytes. Now, before thinking about how to do that, let's just pretend each image can become 2 bytes, and the final file size we get as a result becomes 0.96 megabytes. So clearly we can actually, reduce the file size a little bit by doing things this way, but how is it actually sort of happening under the hood? A very common way of expressing this is to use what is known as R5G6B5. And what that means is, for your red, green, and blue channels, we are basically reducing the number of bits assigned to each. What this means is instead of each channel getting 8 pixels and being able to represent any number from 0 to 255, we are now sort of reducing their range, such that red and blue gets only 32 values to play with, while green gets 64. Now, you might be wondering, why green has this sort of advantage, and there is actually a good reason for this. Our eyes can actually tell apart greens the best, reds second best, and blues the least. And that is why, green actually gets, more levels of detail. Of course, you can also represent this as 5 bits each, and basically wasting one last bit, but doing things this way is of course a little bit better. In fact, if I were to go back 2 slides, the image shown to you here is actually a 16-bit representation. Compare this to our 24-bit definition, In fact, if I were to quickly toggle between the 24 and 16-bit version, well, things look very similar. Let's sort of zoom up and try and take a closer look at what the differences are. So I've sort of zoomed into the background here, and in the 24-bit version it looks perfectly smooth, but in the 16-bit version you may be able to observe a little bit of bending here. As you can imagine, this is extremely subtle, but we can make this effect more obvious by applying it to a gradient. On the 24-bit encoding, things look very smooth, but if we were to use 16-bit, hopefully you can see sort of little bends here and there. However, the differences are subtle at best, and what this means is, well, using a 16-bit representation is indeed a good way to reduce file size. But let's just say, what if we want to take this further? We can, using a method known as indexed color. What we can do is basically generate a palette of colors that, are actually used in an image. Then, for every pixel, instead of actually referencing, the actual color and using a lot of memory to do that, your image just needs to reference colors within the palette. Since this number is probably smaller, you can represent it using less bits. Usually index color is used for 8-bit representations, which means as long as a picture has less than 255 colors, we can use this method. Applying it to the sample image we have now reduced the file size down to 0.48 megabytes. And at first glance, things actually kinda look okay, even though if you sort of stare closely at certain areas, areas like this, you may be able to see some artifacts. So let's zoom in and take a closer look at what's going on in those regions. In the 24-bit version, perfectly smooth, but in the 8-bit version, well, things start to look a little bit strange. Now, I have to tell you something very important at this point, and that is, this graininess here is not a result of the 8-bit representation, at least not a direct result. In fact, this is the result of a process known as dithering. Dithering is meant to actually help us, make the image feel like it has more than just our 255 colors. I'll explain. Let's start with an extreme example in which we take this 24-bit image and basically turn it into 1 bit. Every pixel can only be black or white and nothing else in between. A naive way of doing this will be known as a nearest neighbor selection method. That is, basically every color is mapped to either white or black depending on which one is closer. And in fact, this is the result you get. Nothing like the original, right? Because basically half the circle is going to go to white, as you can see here, whereas the other half, which is closer to black, well, of course, goes to black. However, things don't have to be this bad. If we were to use a method known as dithering, we can actually sort of space out our dots at different levels to sort of create an illusion of, well, the original image. In fact, if you were to stare closely at this, we are only using black and white dots. However, by modulating the spacing between the white and black dots, we create the illusion of shade, and that is what dithering does. With this understanding in mind, we can actually go back to our original image here. Now, I've actually changed things up slightly, and in this image, I've actually turned dithering off. Now, even from a distance, you should be able to see many bending artifacts everywhere. In fact, just to hammer this point home, let's actually take a look at a zoomed up version. Our 24-bit version is of course very smooth, and as you can see, dithering is able to kinda approximate that, even though we're just using very few colors. Whereas if we were to go to the non-dithered version, well, things don't look nearly as good. What this means is, if we want to use a low bit count, we can actually make use of indexed color in conjunction with dithering, and well, things can still look pretty okay. In fact, let's just push things a little bit further, just to see how far we can go. Now, the number here represents the number of colors in each image. 16 million is obviously our original 24-bit image. This is 8 bits, 7 bits, and so on and so forth. And I'm sure you can identify by the broad washes of color that we are not using dithering here. by the time we get down to 128 and 64 colors, that is 7 and 6 bits respectively, you can very clearly see artifacting, so that's not great. However, if we were to redo all these images with dithering, well, we can actually push things a little bit further. I mean, even the 8 color version looks not too bad, especially if you, kind of step back a little and squint. In terms of, what's really possible, I would say we can sort of get away with somewhere between 6 and 5 bits. So what we're going to do is let's redo our calculation using that bit count. If we were to have 6 bits per pixel and assuming no wastage, our image is 2.88 megabits or about 0.36 megabytes, which, I mean, yeah, is a respectable amount of compression, but by no means a great way of doing this. As you can see, well, the graininess is kind of perceptible, so yeah, there has to be a better way. So okay, representing our data in a different way can only bring us so far. So let's take a look at several compression techniques, ways that we can actually make the image itself smaller. So picture this. Let's say we zoom in on a certain segment of data and we realize that, well, it is all 5s. By making use of a method called run length encoding, we can actually represent this in a far more efficient manner. Let's see what that means. First, a little bit of definitions. This is basically known as a run. There are 10 5s here, so this is actually a run of 10 5s. What we can then do is we can actually take note of the run length. Well, we already know it's 10, and what we can do is we can actually represent that on disk. Instead of placing 5 10 times, we can just say, well, there are 10 5s. And as a result, we actually free up the rest of the data. What we formerly used 10 bytes to represent can now just be represented using 2. So yeah, in certain contexts, run length encoding can actually be quite useful. In particular, when you're trying to encode something like line art, something that uses broad washes of the same color, it is very easy to find runs. I mean, the line I just drew out is a run in and of itself, right? So that is just a whole line of the exact same color. Even when we, sort of hit further down to the parts that cut into this telephone here, there are still just a couple of runs, right? I mean, there is a short run of green over here, a short run of white, a very tiny run of green, another run of white, and then a pretty long run of green. Even though this line is a little bit more challenging to actually represent, it still can be broken down to just 5 runs. Regardless of how messy this line can get, it is still better represented as just a couple of runs, right? Instead of a whole bunch of repeated pixels. So yeah, a technique like run length encoding is great for representing something like line art. However, this breaks apart when we have something like a photo. What you see here are the hexadecimal color representations, so don't worry too much about this. The whole idea is it just means that these colors are quite different. At least when measured, there are subtle differences, even though if we actually look at these points, they barely look any different. Don't forget that the basis of run length encoding is that, well, only numbers that are exactly the same will get sort of compressed together. What this means is even if there are subtle differences, which if we are talking about a photo there are going to be, then the whole method actually breaks down. In fact, if we go purely by the definition, if we have a bunch of numbers that are similar but not the same, we actually have to use more bytes to represent it. In this case, we have to say there are 1 of each, to strictly follow the format. As a result, run length encoding may not be the best method for an actual photograph, something that is not line art. Now, run length encoding is just one method. There is another method called Huffman Coding, which I cannot really go into too much detail because it's quite a heavy subject, and we've done a video about this before. So if you're interested to find out more, do click the link on screen. But very much in brief, here's the deal. Elements that appear the most often will be represented with the least amount of bits, whereas things that appear, well, less often can actually be represented with a greater number of bits. So what that means is if we were to sort of pick, 4 general colors from this image, well, clearly green is the most common color, right, in this entire picture. Pink is next, where all the flowers are. Orange, quite a bit as well, here and there. And finally, white is only really present in the background. What this means is, if we were to actually use Huffman coding, what we will find is a pattern like this. Greens will be represented with the least number of bits. And yeah, moving down to less common colors, we can afford to use more bits. So yeah, that's basically the concept behind Huffman coding. And one very cool thing about this is that, well, it's actually tuned to that particular input. In this case, we're talking about images. So we can actually generate sort of the perfect Huffman code for each picture. And that sort of makes it extremely efficient. As mentioned, this is very much in brief. If you want to find out more about Huffman coding as well as how it's actually implemented under the hood, definitely check out the other video on this subject. Now, so far the two compression methods we've used are known as lossless compression techniques. What this means is, no matter what information you actually have, you put that through the compression algorithm. When you actually decompress this information, what you get back is exactly what you've put in. And that is why we say it is lossless, because, well, there has been no loss in information. In contrast to this, we have lossy compression. The idea is, with the same piece of data, we put it through compression. The compression technique actually throws out some information. What that means is your compression algorithm actually goes like, well, you're not going to be able to tell if I throw this out, and so it does. What it reconstructs at the end of the day is slightly different from the original. For example, in this case, clearly no run length encoding can help us here, but if we were to say, hey, 0.1 is really close to 1, let's throw that out, we can then use run length encoding to represent these two together, as well as these two. So yeah, that's the strategy employed here, and it's very important to note that at the end of the day, I will not be able to reconstruct something that is exactly the same as what has gone in. Instead, some things have been subtly changed, and in a way that is permanent. In fact, here's another analogy, just to make things a little simpler. When you're trying to write a tweet and you overrun, the word count, sometimes you'll find yourself changing long words into their shorter forms. That's the same thing, right? At the end of the day, the essence is still there, but you have sort of irrecoverably thrown out some information. So yeah, this is just a little analogy. I don't know how perfect this is, but hopefully it, shows you the whole point behind lossy compression. So that has been lossless versus lossy compression, and the two techniques we've just looked at, namely run length encoding, as well as Huffman coding, are both lossless methods. So yeah, using techniques like this, you can actually sort of further compress your images. So there you go, that was a very quick sort of crash course on image representation. We have barely scraped the surface today because, well, lots of different file formats actually make use of many different cool strategies. For example, JPEGs don't even represent pixels at all. If you're interested to find out more about JPEG, we've done a full video on that earlier on, so look for the card on screen, you can click it, take a look. What else is there? PNG, they actually represent images with a transparency value. SVG, that's another one, which doesn't actually represent pixels as well. Instead, all lines are actually represented using mathematical equations. So that's a completely different approach again. Real-world file formats go to extreme lengths to make sure that you have maximum quality for minimum file size. And so yeah, their methods actually bear learning as well. So what we're going to do on our Friday episode this week is we're actually going to look at several different image file formats. We'll try to understand how they work better, and then we'll compare them against each other, weigh up the pros and cons of each. So hopefully that will be useful to you as well. Anyway, that's it for this particular episode. I hope you've learned something today. But until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.